Hi, back to algorithm strategy class with Megi Wulandari. In this video, we will talk about a technique called divide and conquer. So let's talk about general plan for this technique first. Let's say we have a problem of size n. So by this technique, we divide the problem into several subproblems of the same type and ideally has the same size. For example, like here, we have two subproblems where each subproblem has size of n per 2, half of n. And after we divide them, we solve each subproblem and usually we solve them recursively, which means that we still divide them if we can. And after we have the solution for each subproblem, then we combine the solutions to obtain the solution of the initial problem if necessary. So to divide the problem, we can divide it based on the input size or instances of size n. It can be table, matrix, or others, depends on the problem. Because every subproblem has the same characteristic with the initial problem, divide and conquer usually use recursive function. This is the example of divide and conquer technique. So let's say we want to sum some integers. By brute force, we will have the sum of a0 plus a1 first, and then after we got this, then we add it with a2, and after we get that, we add it with a3, and so on until we reach an minus 1. But for divide and conquer, we can divide it by 2 so that we have the first subproblem and then the second subproblems. We actually can still divide each subproblem into some subproblems as well. So let's see the difference with the brute force algorithm. In the brute force algorithm, we just need to do n minus 1 additions. But for divide and conquer, we also have to do n minus 1 addition, but we also need a process to dividing the integers. So for this case, actually brute force algorithm is more efficient. So not every divide and conquer algorithm is efficient, even when we compare it with brute force algorithm. But this method, divide and conquer, obtains some efficient algorithms that are important in computer science. Divide and conquer also ideally used for parallel computation, where every subproblems is solved simultaneously by their own processor. But to be noted, here in this lecture, we do not consider parallel computation because the computation for its complexity will be different. So let's talk about the complexity of the method divide and conquer in general. If we consider a problem of size n and we divide it into b instances where each instances has the size of n per b, and we have a of the instances need to be solved, if we have such cases, then we can have this as the time complexity. Here we assume that n is a power of b, but it actually doesn't lose generality. Here we have a is how many subproblems we need to solve and what is the time to solve each subproblem. And then here Fn is how much time do we need to divide the problem and then combine the solution. After we know the recurrence relation for our algorithm, we can have the complexity class for the algorithm by using a master theorem. Maybe you already studied it in analysis of complexity of algorithm. So here we can consider the variable a, b, and also d, where d depends on the class of the Fn. So we can say that D is the largest order we have in Fn. So after we get A, B, and D, we see how a relation between A and also B to D. And depends on it, we can choose the complexity class for the algorithm. For example, if I have this as a recurrence relation, then we have 2 as A, and then 2 here as B, and also here, because we don't have N here, then the um, largest order for the Fn is 0. Then we know that A and B to the D, A is 2 and B 2 and also D is 0. So it is equals to 1 such that A is larger than B to the D. Hence we can have this based on this one such that we have AN is in big theta and to the log 2, which is where this is equal to 1, so we have it as big theta n. Let us go to the first example of divide and conquer algorithm, which is a very famous algorithm in sorting called mergesort. So in mergesort, we want to sort array or a list of size n, let's say. And to do that, we can divide the array by 2, and then we solve each subproblem recursively, and then we combine two small instances into one sorted instance. Let us go to the example. So here we have a list of size 8. We can divide them into two subproblems of size 4, and we still can divide them into subproblems of size 2, and we still can divide them into subproblems of size 1. So here we cannot divide them again, so we combine the solution. So the combination must be sorted. Hence, when we have 3 and 8 and we want to combine them, because 3 is lower than 8, we put 3 first and then we put 8. And next, it's same like before. We put 2 first and then 9, and then we put 1 first and then 7, and also we put 4 first and then 5. We still can combine the 4 subproblems into 2 subproblems. So here we start with comparing 2 and 3, of course, because 2 is lower than we choose 2 first. And then we compare 3 and 9 because 3 is lower than we choose 3 first. And then we compare 8 and 9 because 8 is lower than we choose 8 first. And then finally we copy 9 to the array. The same like before, we also do the same with the next subproblems. So here we compare 1 and 4. We choose 1 first, and then we compare 7 and 4. We choose 4, and then we compare 7 and 5. We got 5 to be copied first, and then 7 finally got copied. So finally, we can combine the two subproblems into one final solution. So here we compare 1 and 2, we choose 1, and then we compare 2 and 4, we choose 2, we compare 3 and 4, we choose 3, and then we compare 4 and 8, we choose 4, and then we compare 8 and 5, we choose 5, and then we compare 8 and 7, we choose 7, and because we don't have any comparison in the right subproblems, we can just copy it 8 and 9. Hence, we already got the solution to sort the initial problem. So this is the pseudocode for merge sort. So here we have array A of size n. We first divide them into two sub-arrays and then we do merge sort for both until we get the solution, and then we merge B and C to array A. And here to do the merge, we can always compare and elements in B and also C. Start from the very left element, and then we always compare them and choose the lowest one. And after we choose the lowest one, we move to the right. And then we do it until all elements of B and C has been copied to the A. For the time complexity, here let us recall the general complexity for divide and conquer. Like this. Here, when we have an array of size n, we always divide it into two subproblems of size n per 2, and we always solve both of them. So we have two subproblems to solve, and each subproblem has the size of n per 2. So A and B are 2, and uh, to combine the solution, we need to compare elements in both solution of the subarrays. So to compare them, we need to compare n minus 1 times to finally copy all of the elements to the final solution. So here we have fn equals to n minus 1. Hence we got this as the recurrence relation, and it works for n larger than 1. But for n equals to 1, we don't do anything, so the time complexity is 0. And based on master theorem, we got A equal to 2 here, and then B equals to 2 here, and D is the largest order we have here, which is 1. So A is equal to B to D, such that we got the time complexity class n log n, or we also can write it as big theta. The next example is quicksort. Quicksort is also an algorithm for sorting problems. So here we also have an array or a list of size n, but in merge sort we divide the array effortlessly, but here we divide the array A into two sub-arrays, say A1 and A2, such that every element in the first subarray is not larger than every element in the second subarray. And then we sort each subarray recursively, which means we can also divide them until we cannot divide them again, and then we combine the result. Now, because we have an objective where we divide an array, quicksort have something called pivot. So pivot here is a key to divide the array. So when we're dividing an array A into A1 and A2, the elements of one subarray are not larger than the pivot, but the elements of A2 are not lower than the pivot. So the pivot is kind of the middle value between the A1 and A2. Choosing the pivot can be done in several ways. This is some example of that. So we can choose the first or middle or last element in the array, and also we can choose an element arbitrarily, so randomly, and we can choose an element with the closest value with median. So we find the median first, and then we choose elements that is close to it. So let us talk about choosing the first element as the pivot. So we always choose the first element as the pivot. To do that, we can always choose the first element in the array as the pivot. Let's say here we have AL to AM in the array, and then we do two scanning. The first one, we do it from the leftmost, in this case, next to the pivot, to the rightmost of the array, until we found an element that is not smaller than X, and we name it AI. And the second scanning is goes from the rightmost to the leftmost, and we find something, an element that is not larger than the pivot, and the element is then called AJ. So after we get AI and AJ, we see the index of them. If I is less than J, or on the other word, if AI is located on the left of AJ, then we swap AI and AJ, and then we continue the scanning. But if I equal to J, so they are in the same position, in the exactly same position, then we already obtain the partition. And then if I is larger than J, so AI is located on the right of AJ, then we swap AJ and the pivot, and then we already got the partition. Let us go to the example. For this, because we always choose the first element as the pivot, we choose 5 as the pivot. So we do a scanning. I use a blue color for this, from left to right, and searching for element that is larger than the pivot. Because 3 is smaller than the pivot, then we go to the next element. 1 is still smaller than the pivot, so I go to the next element and I found 9, which is larger than pivot, so I got AI. And then I do the second scanning from right to left. I use the color red for this to find an element that is not larger than the pivot. So here, because 7 is larger than the pivot, we go to the left, and 4 is smaller than the pivot, so we got AJ. Here we check the location of AI and AJ. Because I is less than J, so blue is located on the left of the red, then we swap the element. And then we continue the scanning, so we move the blue to the right and then red to the left. Blue want to find an element that is larger than 5, and red want to find element that is lower than 5. And we already got them in the next scanning, such that we got AI and AJ. And again, because blue is located before the red, then we swap them, and then we continue the scanning. And again, blue meets an element that is larger than 5, and red meets an element that is lower than 5. So we got AI and AJ, but now, because red is located before the blue, we swap the AJ, or the red one, with the pivot, like this. And because we already swapped the pivot, we can divide it into these subproblems. So pivot stand by itself, and then we copy elements that is located after the pivot, and also elements that is located before the pivot. Okay, and then next, we want to solve the first subproblems. Here we again choose the first element as the pivot, which is 2, and then we do the 2 scanning. Blue is from left to the right to find elements that is not smaller than 2, and then the red one is goes from the right to the left to find an element that is not larger than the pivot. So here blue already met 3, which is larger than 2. So we got AI, but red need to move to the left side, so it meet 1, which is lower than 2, so we got aj equals to 1. Here, I is less than j, or blue is located before the red. So we swap them and we continue the scanning. We move the red to left and blue to the right. And again, the blue meets an element that is larger than 2, and red meets element that is lower than 2. So we got AI and AJ, but now because red is located before blue, we swap red with the pivot like this. And because we already swapped the pivot, we already got the partition. And again, here 3 and 4 still can be divided. And here we again choose 3 as the pivot because it is the first element. And then we scan um, and then we search AI, which is larger than 3 from left to the right. And we found 4. And then we search for an element that is not larger than 3 from right to the left, and we got aj equals to 3. And because I is located after j, so we swap aj and the pivot. But actually, aj is equal to the pivot in this case, so we do not swap anything. And we got the partition. Next, we want to solve the last problem. Here we again choose the first element as the pivot, which is 8. And then we do the two scanning. Again, blue search for an element that is not lower than the pivot, and we already found 9 for that. And red, from right to left, we search an element that is not larger than the pivot, and we found 7. So we got AI and AJ directly, and because AI is located before AJ, we swap AI and AJ and we continue the searching. And because here blue again found an element that is larger than 8 and red found an element that is lower than 8, then we again found AI and AJ, but now it's time to swap the AJ with the pivot. Okay, because we already swapped the pivot, we already got the partition. And here, because all of them has been solved, we already found the solution. But here, let us consider a case where I have 9, 7, 8 instead. So in this case, x will be 9, the pivot will be 9, and then I start searching for AI from here. But because 7 is lower than 9, we go to the right element, but because 8 is also lower than 9, we haven't got AI until the end. In this case, we can think about an imaginary element, let's say a very big element, or we can say it as an infinity. So we can say that AI is that imaginary element. And for AJ, we search it from the rightmost element, and we already found something that is lower than the pivot. So we got this as AJ, but because AJ is located before AI, then we swap AJ and the pivot. So after swapping, we already found the partition like this. So it is divided into two problems like this. Okay, now this is the pseudocode for the quicksort. So here we need to do the partition for an array that we have, and then we do quicksort for both of them. For the partition itself, we can always choose the first element as the pivot, and then we do scanning from the left for one and the other from the right, and we search for something that is not less than x for one scanning and something that is not larger than x for the other scanning. And if the location of the first one is less than the location of the next one, then we swap them and we continue with the scanning. But if not, then we swap the AJ and the pivot. Now, if we consider the time complexity for a quicksort, it depends on the size of subproblems we got from the division. So here for the best case, we always obtain subarrays of the similar size, which means we divide it by 2 and we always get 2 subarrays of size n per 2. So this is the size of each subarray and we need to solve both of them, and then to divide and combine the solution we need to compare n elements. So yeah, this is the recurrence relation we have. It works for n larger than 1, but for n equals to 1 we do nothing, so the complexity will be 0. And based on master theorem, we have A equals to 2 here, and then B equals to 2 again here, and then D equals to 1, the largest order we have here. So based on the master theorem, because we have A equals to B to the D, we got this as the time complexity class for this algorithm for the best case. But for the worst case, if we get an array of size n, we might only divide it like this. So this is of size n minus 1. And again, n minus 1 will be divided into 1 and n minus 2 and so on. So we do not really decrease the size of the array we want to sort. We can found this case when we have the input array that has already been sorted. So this will be the lowest element in the array. So AI will be located here on the first search, but AJ will not find it until we go to the first element, which is the pivot, so that we need to compare n plus 1 times to do the partition. And when we already have an array of size n minus 1, we do the same. So we need to do n comparisons and so on until we have array of size 2. We need to do 3 comparisons. Hence, we get the time complexity class of big theta n square. And then for the average case, we may have any size of the subarrays. It can be anything between 0 and also n minus 1. In that case, we need to solve the first subarray of size s and also the second subarray of size n minus 1 minus s. And then to do the partition, we need to do comparisons, which can be done in n plus 1 times. And then let's say we consider the same probability for the size of S. So we search for the average of this value. And this work for n larger than 1 because if we have array of size 0 or 1, then we do not do anything. So the time complexity will be 0. The last one we talk about in this video is binary search. Binary search is used to search an integer inside an array that has been sorted in non-decreasing order. So here we need to check if an integer x exists in the array. If yes, we return the index of x in the array, or otherwise we return -1. So if we have an array A of size n, we need to check an element that is located in the middle of the array. And we check if it is equals to x. If yes, then we already found the solution. If no, we see if x is larger than the element. If yes, then we need only to consider elements that is located after the middle position, because we already have a sorted array. Or otherwise, here we only need to check elements that are located before the middle position of the array. For an example, here we have a list of integers and we want to search x equals to 70. So here we have 13 integers in the list. We found the middle position, and then because 55 is less than x, we only need to consider elements that is located after 55. And here we have a subarray of size 6, and then we check the middle position for that, which is 81, and then 81 is larger than 70, so next one we only need to consider elements that are located before the 81. And next we have a subarray of size 2. We check the middle of it, which is 70, and it is equal to x, so we already found the solution. This is the pseudocode for binary search. So here we only need to consider low, high, and mid. So low is the lowest index of the array we are solving, and high is the highest index of the array we are solving, and mid is computed like this. So it is the midpoint from low and high. And then we check if the element in the position mid is equal to x. If yes, we got the solution, and if not, we check if x is less than the element. If yes, then we need to consider what we have on the left of that, or otherwise we check what is on the right of the element. And if we don't find x until the end, then we return -1. So for the time complexity for binary search, let us recall the general complexity for divide and conquer, which is A, T, N per B plus Fn. Here, we divide the subproblems into two subproblems of size n per 2. So B is equals to 2. And then A, how many subproblem do we need to solve? We only need to solve one of them, so A equals to 1. And then Fn is the time we need to divide and combine the solution. We don't need anything to divide the problem and combine the solution, so it is equals to 0. Hence, this is the recurrence relation for that. And then from master theorem, again, because we have A equal to 1, B equals to 2, and D equals to 0, then A is equals to B to the D. Hence, we got this as the time complexity class for binary search. As a remark, here we discuss binary search as a part of and conquer algorithm, but actually not everyone agree with that. In Anani Levitin's book, binary search is not included in the divide and conquer chapter. Instead, it is included in a technique called decrease and conquer. Also in the lecture slides from Rinaldi Munir, it is stated that binary search is not divide and conquer algorithm. But here we follow the book from Richard and Napolitan and also other sources from prestigious universities that says that binary search is part of divide and conquer algorithm. The difference in the opinions actually occur because in binary search we divide the problem into two sub-arrays, but then we only solve one of them. And many believe that in divide and conquer, we need to solve each subproblem we have. But those who think that binary search is a part of divide and conquer algorithm think that after we get two subproblems, actually we want to solve both of them, but one is already solved, so we only need to continue with the other one. To read more about divide and conquer algorithm, and there are a lot of other examples for this, you can search for these references. Okay, that's all for this video. Thank you for watching and see you on the next video.